questions, because that's where I like to start. I can't work with nothing. We don't have time to cover the entire 2 chapters you guys have learned. So, I'm expecting that you guys can tell me, really, I don't get this, or I don't get that, so I can know how I can help you guys.
So what we talked about earlier about the characteristic and the brainstorming, where I said I didn't know where that was happening at.
Yes.
I would like
You wanna
to
go over this? Characteristic and Bremshaw stuff. Okay, we'll talk about how we create that.
and where it comes from.
Got you. So I guess we'll start with that chapter, right?
Yes.
How's that? Everybody okay with that?
Yeah.
8, X-ray production. Okay, so I guess you guys can pull up your PowerPoint. I'm gonna just open it, one that she has in Moodle. Again, I can't share it, so I apologize. But anything, I'll be drawing. Gosh, it's cold, y'all.
Oh, my jelly.
I'm not used to cold. I'm in Texas. It's like 100 and something odd number degrees every day. So this sucks. Although, when I lived in California, I did like the weather. It wasn't too hot. Even though people in Sacramento always complain how hot it was. I'm like, I know hot now.
This year's back, it's been like so many days over 100
It
days.
is. It's been a nightmare for everybody apparently in certain pockets of the country. Okay. Is there a spray? I hope this works. If there is a spray. All right. So let's start with what? I need a marker. I just have a little show. Okay. Characteristics. So how about I'm gonna ask a question, see if somebody can tell me something. Okay. So I think I had a question about the whole production of the X-ray. So who can first tell me, what do we need to produce X-rays? We need certain things to take place in order to make an X-ray, right? This is what you got. You've seen the X-ray tube, right? I'm not a good artist, so it's gonna be funky. Expect that. Here's our patient. Here's our lovely table, right? Now within this X-ray tube, you've got this whole filament, you've got the focusing cup around it, right? Again, I'm terrible, so it's the best I can do, I'm so sorry. Here's our anode, right? We got all the fun stuff. My tube is getting really small. It should be a bigger box. But you guys can follow along with me. Filament, focusing cup, anode, okay? So what do we need to produce an X-ray? The book tells you need 3 conditions, but describes it as a condition. That sounds like a physical problem, right? Like a condition.
Filament, you got electrons.
We do need a source.
Source of energy, electrons.
We need our source, right? So you need 3 things. You should know these.
Yeah.
When I say that, I really mean it. Like, it'd be like, you always say, like students say, I don't know what to say. Well, if I say you should know it, you should know it. Because Christy wants you to know it too. So the first thing you need is a source. So we need a source of electrons, right? I abbreviate a lot, so I will try and tell you what that is. So what's the source of electrons? That's the process that's taking place. So I like it.
It's hard.
No, that's,
Oh, wait,
no,
no.
that's shit.
He said thermionic emission. Go where he's going.
Cathode. Or
Cathode. What part of the cathode? Cathode is made up of what? See, I'm going back to the other chapter because you need to know that in order to get to this point. Again, it's a story. So Phil, he said thermionic emissions. He said cathode. What's up? What's part of the cathode? That was part of the X-ray tube chapter.
Filament, right?
Filament. What else?
focusing.
Focusing
There we
cup.
go. That's your cathode. Filament and focusing cup. So those electrons came from here, didn't they?
Yeah.
You boiled them off in that process of thermionic emission. Right? That's literally the boiling off of electrons. So electrons have left this. I'm going to draw a bigger filament over here. If I break this, I'm out. I'm blaming somebody else.
No.
It's on Jesse.
Blaming somebody.
It's the closest.
Okay. So all your electrons are here, right? What's they say that cloud is called?
Thermionic emissions.
That's the process of boiling off electrons. What's the cloud that they form?
Space
Space charge.
Space charge.
That's the way you gotta keep going, reviewing every time. Remember, what do I know? What do I know? That's what you gotta ask yourself. So these electrons are boiled off. So we got our source of electrons, it's the filament. Okay. So what else do we need to produce X-rays? So we got the source of electrons. Right, so we do need KVP, but what do we don't just say KVP, because we didn't say MA. MA is what boils these off.
Kinetic energy.
Free electron?
Right, there is kinetic energy. They come from KVP. What'd you say?
I said free electrons.
Well, they are free, technically.
Alright.
They're floating around. But we need, you said KVP. I want to build up that word KVP. KVP is giving them some kind
Energy.
of, right, it gives them the kinetic energy. I think you said that too, right? But we describe that as the force, right? That's the force. That's what gives them that speed, that kinetic energy that we're talking about. So you also need a force, which is technically our KVP, or you can describe that as our kinetic energy, right? So, you applied your KVP, because our MA is what boiled these off, right? You learned that in the circuit. That's why you had to learn the 3 parts of the circuit: filament circuit, high voltage circuit, and operating constant. So we boiled up our electrons. These electrons need to move, right? That's what the KVP did, give them that kinetic energy. So now they moving. They're moving to hit this. What's that? Anode. What is another word that we use for this word, anode? Focal track, sure. There's a lot of words, right? But we also call it the target. Right? So you need a target. It needs to bump into something. The target is our anode. So these electrons boiled off. We hit the KVP, and it forces them to go towards the anode, right? Because we know electrons move from negative to positive. The filament is a negative, isn't it? Negative charge. The voltage, the KVP you select, is what causes this to take on a positive charge. Because it's the kinetic energy. That's why they're now attracted to them. You learn that in boring electrostatics lecture, right? So now, we hit the target. So these electrons now are bombarding this target anode. And what happens when they hit that anode?
Yeah, decelerate.
Right? So we can say, here, we can break this down to acceleration, right? Which is our, I'm having trouble with words today. And there's also deceleration. It's all happening right here, this target. They're accelerating towards it, and they're decelerating. Right? That's what's happening. But when they hit this target anode, that's when we create those target interactions. That's what that chapter was in Bouchon, I think Carlton also describes it as that. Let's see what slide that is. He describes them as target, I think, interactions too. Yep, target interactions, not crazy. So once this happens, we create different target interactions. So you have to remember, what does that mean when I say target interactions? Remember, every single thing on this planet is made up of millions of atoms. That's why you had to learn all about them atoms. I know, it's like, why? I'm learning this. But there's a billion atoms inside here. And they all have little, shells, right? That's what y'all learned about the atom. So these electrons are interacting with the atoms in this target. That's what they're targeting. Okay? So once they interact, I should draw something inside here, right? Once they interact, 2 things are being produced. That's what this chapter is about. Target interactions. What interactions are happening inside this target? 2 things I can tell. Don't be afraid to answer something. You learn from being wrong.
It's creating heat and X-ray.
Ooh, bingo. Say it again.
Heat and X-ray.
Woo! Say it again. I'm about to start preaching in here. I love physics. Okay, anyway. So we created heat and X-rays. Those are 2 interactions. How much of that is heat?
99.
Everybody better not miss that question on the test, I swear. I will fly over here and hurt someone.
So it's on liquid.
So 99% is heat, right? So we're producing heat, and we produce X-rays. 99 and 1%. Most of all this that happened was making heat. That's why that tube gets hot. That's why we gotta be careful not to make sure that you don't place the patient's body parts on it, because it will burn them. So it could burn you too. It's happening. So this is a really inefficient process. You've probably seen that written in the book too. Very inefficient. Why am I saying it's inefficient? Because most of the energy is not heat. That's a waste. We need to make X-rays. Well, only 1% is X-rays. Okay. I'm gonna come back to that. The X-rays that are produced, there are two types. What are those? What's this chapter about?
Bremsstrahlung.
Bremsstrahlung and characteristics. So this is Brems, and this is characteristics. Right? 99% is heat, 1% is X-rays. These X-ray photons that are coming out are either going to be characteristic or they're Bremsstrahlung. And this is all happening inside this lovely thing we call an X-ray tube. That's why it's called X-ray production. It's being produced in the X-ray tube. You will learn later about other interactions that happen in the body. You have to be able to distinguish them from this, because you guys are going to remember this as you're learning the new thing. Right? Everybody still with me?
Yes.
Who's not with me? Tell me if you're not, because I'm going to keep moving. Say it, say it. Speak now, forever hold your peace. Okay. Who can tell me how heat was produced? Because you should know that. You need to know everything that I've done here so far. Okay. So who can tell me how is heat produced? How exactly did that heat get produced? If Christy said to describe heat production, how would you describe it? What happened to make it so hot? What was the interaction? Those electrons left this filament and interacted with the target atom, one of these. Where? Where in this atom? Was it the nucleus? Was it the inner shell? Was it the outer shell? Was it in space? Was it at Nathaniel's house? Timothy's car? What happened?
Inner shell, right? Cage shell, right?
Not yet. You're on the right. You're close. Hot and cold, we can do that. So these electrons, well, any of these guys, because remember they're leaving the filament, right? They interact with an atom in basically an outer shell. It just causes them to get excited, right? You had to learn that. It's in there, it tells you those electrons interacted and it just causes them to be excited. Everybody was in, everybody, I was about to say, was you ever in elementary school? But everybody was in elementary school. And you know, well, I'm gonna describe my situation. So if a boy liked me, he would hit me and he would run and I'd be so excited. He'd be like, hey, Lexi. Nobody. Gosh, you guys are so great. Well, I was excited when I knew somebody liked me. Anyway, excitation is what happened. Reason why I'm emphasizing that is because I want you to know it's not the same as ionization. Okay? Heat is produced because of excitation. That electron, what we call filament electron, it can be referred to as an incident electron. You've seen that also in that picture that you look at. This kind of has a lot of names. Okay? So it causes it to get excited, meaning it releases some energy, but energy in the form of heat, thermal. Okay? Then it goes back to its original state. And that's how we got heat. Any questions on how we produce heat? So who want to tell me what I just said? Take a shot.
So, the filament electrons get excited, that's where heat is generated to hit the anode targets.
Pretty much. The end. Anybody not clear? It's gonna be a pop quiz at the end. No, I hate those. Don't be Christy.
So the process is called excitation?
Mhm.
That's when the electrons are excited and
This
move?
electron interacted with likely an outer shell, because if you guys remember, the further that electron is from the inner shell, the less tightly bound. It has a lower binding energy, right? The inner shell is really tight, right? So these can interact with these outer shell electrons. There's a million electrons in orbit, right, around these orbital shells. So you have to remember that with an atom. You can't forget that. That's the reason why we learned all about that atom. That's why we have all those shells. Why? Who cares what was K? Who cares what L is? It's always a reason. So this electron, this filament electron, interacted with likely an outer shell, and it just caused it to get excited. It didn't knock it out of the shell, right? That's what ionization is, ejection, removal of an atom from its orbital shell, right? That's the definition of ionization. But ionization didn't happen. Excitation happened. Just got excited. It's like a little love tap.
So it happens comes from the filament to the anode, and it happens at the, okay.
Yeah, you got it. Okay. You sure?
Yeah.
Don't lie.
Nah.
Now we're moving on to X-rays. Two types. Okay. Characteristic and Bremsstrahln. I believe that's the picture. Which one do you like first? I'm gonna go with C because that's the start of my name, so we're gonna start with characteristics. Okay. Characteristic X-rays happen how? Who thinks they want to take it describing that? Not you, because you just did one.
When an electron hits another electron.
Another one? Who's
Or
another one? There's a bunch of them.
Another electron.
On the,
from the
K
from the
shell.
From the right shell? Yes, from the K shell. So, a filament electron interacts with an inner shell, specifically K shell. What does it do when it hits that K shell?
Ionizes it.
Right. So, knock that out. I'm gonna test these things. No, just kidding. So, ejected that K shell electron. What happened when that K shell electron got ejected? What's next?
Outer shell.
The cascade effect.
Cascade effect.
Good, but describe the cascade. It's nice that you can tell me that, but what is it? Now break that down.
An electron from the outer shell replaces it to the inner shell.
Good. And when that outer shell electron replaced that inner shell electron, that is when we produced that characteristic X-ray photon. So if I draw this filament electron, right here's K, L, that's enough for now. And here's our electrons in our K shell. So when this ejects that inner shell electron, he's gonna keep going because he got kicked out. So what happens is you got a vacancy, is a space open, right? If that was Beyonce in that inner circle, I want Beyonce, give me it. K shell, that's what B is, okay? I'm a big Jay-Z fan from New York. You ain't know that, you knew. That was Biggie too, you ain't know. You see? Feeling it right there. Okay. So that void needs to be filled in. It's unstable by having an electron knocked out. Right? You guys don't know all about that radioactivity. Right? So as Timothy, was it Timothy? No, it was Isaiah. Esau.
Jesse.
No, it's not. Okay, so when that, any outer shell, and typically it's usually the neighboring outer shell, but it can be anyone, okay? So let's just say the L shell electron is gonna fill that void. But when the L shell jumps into that space, you produce a K characteristic X-ray photon. Right, and I'm gonna draw one in each of these, and I'll draw one more in. I said if the L shell replaces this K shell. So let's just say I need another color. Let's say L replaces K. Which photon is this going to be? What do we call this photon that was created from this energy? Which shell? You want to
K.
call it a K or a L?
K.
What? What? There's only two choices. Which one?
Let's say K.
You still saying that?
Yeah.
It's the right answer. Don't change your mind because I told you to. So that's why multiple choices. You saw too many choices and you're like, maybe. No, you know what you know. Don't change your answers. Don't change them. So it is a K shell. What if the N shell electron filled in that vacancy in the K shell? What kind of characteristic X-ray photon is being produced?
Still a K shell.
Okay. That's exactly what it is. It's still a K characteristic. Whichever electron was knocked out, no matter who replaces it, it's still going to be that shell's. So I don't care if P filled in for K, it's still going to be K characteristic. If L shell was ejected, right? L shell was ejected. But M will fill in the vacancy for the L that was ejected. What characteristic photon would be produced? L. So whoever got ejected, that is the shell characteristic photon. Not who fills it in. Everybody still with me? Okay. So, why do they call it characteristic X-rays? You should know that. What's the point? Why do they call it Charlene's X-rays? Because I'm the one taking them X-rays right now. Why do they call them characteristic? What's so characteristic about it?
You've got to do.
Forget to have like a defined energy or KEV.
We're on the right track, but not KEV.
It's not. Yeah.
I feel like you know what you want to say. I just
I don't
can't
know
get
the
it.
word,
Come on. So, I'll tell you. It's characteristic of the target material. Remember, you guys learned characteristic X-rays are produced at what KEV or KEV? What's the minimum needed to produce a characteristic X-ray photon? You had to know that.
69, yeah.
69. What was the target material of the anode in radiographic tubes? What's it made of? Tungsten. Tungsten is the characteristic material, target material we're using, right? That's why you had to learn that material is tungsten. So, characteristic X-rays are a characteristic of the target material. That's how they get their specific values or energies for each shell. K shell is 69 because it's tungsten. If it was gold, right? If this was gold, it would be a different characteristic K shell photon produced. Oh, I love that. Now let me, I want to show you all of my moves. I'm not gonna do it. Okay? Anybody with any questions?
So you said that the minimum KVP is 69,
Only for tungsten,
only for tungsten.
because that's what we use in our X-ray tubes.
But that's different from like when we do hands and it's like KVP is like 60.
Oh, so no, you're thinking about the KVP we select on the console. That's the
Okay.
amount of energy we need to pass through the patient. Now, that's different.
Okay.
That's quality quantity, which I think we'll talk more about that, I think this week, tomorrow. But we will dive into that a bit more. What I'm describing is every type of X-ray tube that's created, whether it's dental, whether it's mammography, ours, they all use different material in them to produce X-rays. The one that's in our tube is tungsten. So the photons that are going to be produced, our characteristics are based off the tungsten target. So the minimum KVP you need to produce a characteristic X-ray is 69. If you had 55 KVP, you won't make any characteristic X-rays because you don't have the minimum amount. Everything in that photon will be bunched along, which we didn't get to that, I kind of jumped ahead. Any questions? Okay. What else should we know about characteristic? You need to know. Oh, if you had to determine the amount of energy, how would you figure that out? What if you had a question that was a mathematical question where you had to calculate?
Split it in.
Subtract two.
The differences between two shells that are the replacement.
Bam! That's it. That's it. Say it again. Say it again.
So the difference between whatever shell's replacing the K shell.
Right, so if it was the L shell that replaced the K shell, then you would take the difference between the L shell's binding energy and the K shell's binding energy. You subtract the two. And that's how you find out the amount of energy that went into making that characteristic photon. I think there's a math problem or two in your text. Maybe one, not a lot. Okay. All right. I think we're done with characteristic. Let me make sure I ain't forget nothing.
Me too.
Okay, so this is something, what slide is this? I'm sorry, I don't know, because they don't have numbers. Anyway, oh wait, I think it's slide 10. Is that 10? Yep, slide number 10 on X-ray production, chapter 7. You'll see there's a list of binding energies. I don't know if you guys have access to it right now, but you'll see that there's a number of binding energies that she posted in that slide. Right, so you see K shell is 69.5, because that's the minimum we need for K shell. That's the binding energy. That's how much energy is required to remove that K shell and that electron from that orbit. Okay. So any X-ray photon has to have that much energy in order to produce this. So if we selected 90 kVp, do you think you could produce a characteristic X-ray? You sure could, because it's more than 69.5. Usually, sometimes you might see 70. You won't see both choices ever on a test. That's just unfair. Because it depends on what kind of book you read. So 69, 70, go with what you see. Right? Like I said, what if I had 69? Could I produce a characteristic? Yeah. 55?
No.
No way, player. You ain't getting in this. Okay. So I'm sorry, I don't know who said what. I don't need y'all to sit together. That would not be acceptable. Till I remember who's who. Okay. So if this was 69, as we said, K shell is, and then that slide tells us that L shell has a K binding energy of 12, what would be the amount of energy that created that photon?
56. 57.
57. Because if L replaced this, the amount of energy it took to jump into that space is what helped to create this. So that would be how you had to find it if you see a question about something. All right, let's see, what else is here? What else is here? So yeah, her slide number 12 talked about that heat. That's what that lovely picture is, where you see all those vibrations around those electrons. That's excitation from heat. That's definitely from Bouchon specifically. Okay. Next, breaking. Everybody cool with this one? Characteristic? Okay, going away. All right. Bremsstrahlung. What does that mean?
Breaking.
Breaking. Right.
Nice.
Can you spell it?
No.
It's okay. I was typing it all wrong today myself. I know how to spell it though. And when we do it, just to say so.
Yeah.
All right. Anyway, Bremsstrahlung means breaking or.
Break.
You can't say
This
that.
guy.
This guy. This guy. No. Begins with an S. Don't say that one. Mm-hmm. Sure you didn't. That's my Bernie Mac voice. Slowing. Right? Slow or breaking, right? So if you saw, what if you didn't see breaking as a choice? What if you don't remember breaking? Remember slow, right? All right. Remember, they always use different words. That's what makes students think they're being tricked.
Okay, so the 85% and the 15%, what does that have to do with the characteristic and then Bremsstrahlung?
It's a great question. Great question. Does anybody think they can answer that? The question is, there was something mentioned about 85% and 15% of the amount of X-rays being produced. Anybody think they remember what that is? Okay,
Bremsstrahl's 85%, characteristics was 15.
good, you got it memorized. What's it mean?
So
Good.
like Bremsstrahl uses like lower KVPs, so they're capable of making more of the X-rays. Oh no, sorry, with less of the KVPs.
It's only more or less, we only got
Oh,
2 jobs.
no.
Or less. Or less. You're somewhat on the right track, but not exactly. So basically what's happening is, I just told you about the amount of energy, the minimum amount of energy we needed to produce characteristic. We said that number is,
69.
so if we don't have an energy of at least 69, then that means anything lower than that would have to be a Bremsstrahl photon, because you have to have at least 69 to produce characteristic. So if those photons don't have a KVP of at least 69, none of them can't be characteristic. Because I asked you guys, what if I have 55 KVP? I'm not making no characteristic. Not one photon came out of the characteristic. So that means all of those photons had to be the other guy, Bremsstrahl. Okay? So that's why they say there's a percentage, because there's a certain amount of X-ray photons that's going to be produced in this whole tube at any given point in time. 15% of them will probably be this. The other 85% is this, because this is the majority of the X-ray photons you will produce. Because not every X-ray we use 69. Some you might be, well, back in the day we used less. Now we don't. But some of them will be less than 69 keV. Every photon that's being produced, you have to remember, there's so many atoms in there. Tons of them, hundreds. And all these filament electrons interact with any of them. You can even interact with multiple at the same time. That's how we produce all the photons that's come out. How many times have you heard one of your instructors mention the beam diverges? You don't see it, but you keep telling me it's going verge, it's diverging, right? That whole inverse square law, spreading out. But that's because there's a ton of X-ray photons coming out at a given time, because they're all interacting with almost every atom that exists in there. Does that make sense? Anybody not clear? Is that?
So you said 15% of the time it's gonna be characteristic, and then 85% is gonna be Bremsstrahl.
Mm-hmm.
Okay.
Because remember, you need to have at least 69 to do this. If the photons are not of this energy, then that means everything else has to be this. So this is always the majority. Because not every photon has the same energy. Every photon has a different energy. Because the filament electron, all of these electrons don't have the same kinetic energy when they move. This one might have 1 keV of energy. This one might have 15, this could have 20, this could have 100. They have different degrees of energy. They're being boiled off. They're being boiled off at different energies. All right, so let's move to our Brems. Gosh, I should have chosen a different color. Green's so light. I watch you do that and you don't say nothing. Jeez, you guys are the worst. No, you guys are good. Okay, here's Bremsstrahl. Jeez, that looks really bad. Oh my God, you guys, they just watch me do this worse and worse. I can't mess with y'all. I'm gonna also get rid of this. That's my bad. All right. So, Brems we said means breaking or slowing. So again, still the same target anode. That's why we keep drawing these circles, right? That's why your book keeps showing you a million of them. Okay, so we know this is our K, L, M, and I'm just drawing it in just for the sake of it. There's our filament again, our electrons coming off the filament, right? That's where they're coming from, right?
Mm-hmm.
Filament electron interacts with what shell?
Okay.
Outer shell, K shell, K shell. Who else? L, remember L? M, N, O, P, going once.
So it just goes through the nucleus?
Ooh, no, not the nucleus. Bremsstrahlung interactions, they don't interact with any shell. That was a trick question. It wasn't a trick question, just you guys were thinking it had to be a shell. Bremsstrahlung X-rays, it means it slows or is breaking. So it didn't interact with anything. It just got close enough to the nuclear force field, this is our nucleus, that it was influenced by the strength of the nucleus. Because electrons are naturally attracted to the nucleus, right? It's positive, right? Protons, neutrons. So these electrons will go in and they don't interact with any of these shell electrons. But they can be influenced by the nucleus. That's what causes it to slow down, right? It's like when you guys are doing like 90 and then you gotta turn the corner and slow down. How many of y'all be doing that? Don't answer that. Oh, that was a trick question.
No.
Jeez, Brad. Are you kidding me?
No
Dangerous. Don't do that. All right. So it gets so close that it's influenced, and that's what causes it to slow down and break and change directions. That's how it does that. So it didn't interact with any shell. So Bremsstrahlung, no shells. It's influenced by the nucleus, the strength of the nucleus.
So where does the electron go off to then?
There is no electron it interacted with. There's nobody, everybody's in their space. You mean this filament electron?
Yeah, it's going on
Oh,
electron.
it goes to just be a free electron and it's going to interact with probably another atom because it still has energy, right? It came in with some type of kinetic energy when it left. So it got so close it lost some, but it goes in a different direction. Just like when you're driving and you got to turn. You got to slow down unless you fast and furious. Anybody? Do not do it again.
Not me.
Do not say it again. So it has to slow down. So that's what causes it to do so. Okay? And in this process of slowing down, it loses the energy. And that energy loss is your Brem's photon. That's how you got that. Okay. So, I believe your Carlton book shows you like 2 different ones. That's one, and then I'll draw one over here. I didn't want to make it another color because you probably won't see it. It's actually red, but I'm already using red. Right, so this is one, right, super close, and this one is a little further away. Everybody see my 2 photons? So let's call this guy Brem's A, and this one we'll call Brem B. This will be my rap name. Okay. I can't rap for my life. Okay. So, notice I've drawn them and they have 2 different degrees of deflection. This one is pretty dramatic, whereas this one, imagine it like this. This photon was literally moving in this direction, but it was influenced and it changed this direction. But that's where it was going. I was supposed to be going straight, but something made me swerve a little bit. Whereas this one, it was going in this direction. It should have kept going straight. It should have, but it didn't, and it went way off that way. That happens because of the strength of that nucleus. The closer that photon is to the nucleus, the more energy it's going to lose. That's why this one has such a dramatic change in direction, because it got too close. It's like messing with the bouncer. Back up. I want to be a bouncer. I want just like Hulk. Okay? So this one would be described as a high energy Bremsstrahlung photon because it lost so much energy because it was dramatically influenced by the nucleus. Whereas this one would be described as lower energy because it was barely influenced. It was a small change of direction. This one was, if you had to draw an angle here, this one is huge compared to this one. So summary is Bremsstrahlung photons are influenced by the nuclear force field. Okay? It's that slowing or breaking. In that process of getting influenced, it will lose its energy, creating the Bremsstrahlung photon. Now, do you necessarily have to know if it's high or low? Honestly, I don't know. Maybe, it's possible. I don't know what questions you're gonna have. But, just in case, you'd be asked, right? So, would you guys be able to draw that if you had to? Would you be able to describe it if you had to? That's what you want to be able to do. Let's see who else I need to talk about. I think those are the 3 interactions. So, what should you remember? What are the interactions that are happening? How many are there? 1, 2, 3, 4. How many interactions we got happening in that target anode? Anybody?
3. You have heat and then the 2 X-ray types.
High five in the air. Pop, pop, pop. 3 interactions. Heat, which is what percentage? 99.
99.
Characteristic and Bremsstrahlung. Those 2 are your X-rays. The 1% that make up X-rays. Characteristic and Bremsstrahlung. Okay. Of that, 85% of those photons will be Bremsstrahlung. 15% of them will be characteristic. Let's see what else we need to talk about. $75, $70, characteristic cascade. You guys get that what that is already. That's pretty much it. Oh, there was a question. So she did have in her PowerPoint an example of how to calculate characteristic. So go over that. That was slide number 31, just in case you're asked something similar. Oh, okay. So we're almost done with this. I don't even know if we're done this time. I'm lying. Let me not say that. Okay, the spectrum, really quick. I'm going to talk more about this tomorrow, but you guys reviewed that spectrum. Anybody know what the X-ray emission spectrum is?
Can I say that one more time?
The X-ray emission spectrum. Anybody remember what that is? I think I'm on like slide 30 something right now. There's like 65 slides in there. Yes, the graphs.
Ah, yeah. Oh my god.
If it's in that book, it's important. Always ask yourself, why did they put this in here? What for? Because they want to stress me out? That's possible. Why did they do it? I don't know. Physics people are complicated. Y'all better learn to love physics after me, I swear. I better be like, I love it, Miss Seeley.
Yep.
You were the bomb.
So far.
Oh man, I'm on a trial basis right now. Alright, here we go. So our X-ray emission spectrum is graphs. Okay. Now, here's our spectrum. What's on the x-axis?
Let's see the photons.
Energy,
Photons.
not photons. Oop, gee, what? If you wrote photons, I'd mark that wrong, because that's not correct. If you had to write that out, that would be wrong. It's the energy. Even if you wrote KeV, I'd take it, because that's still energy. Oh my, this thing is not your friend today. What's on the y-axis?
X-rays.
X-rays, what do you mean?
Um,
You wrote X-rays, I gotta mark it wrong, that's not telling me anything.
Number of X-rays.
Number of photons, right?
I didn't know what the question was.
Oh, sorry. Okay. Right. Now, we said what percentage of, before I do that. You learned that the X-ray interactions can be described as, each of the X-ray interactions for photons can be described as one of two things. They can be described as continuous, right? You heard that word? Or you described as discrete. Why? Why do they use those words? What does that mean? Always ask why. Why? Why? You ever watch that movie with, what's his name? Austin Kutcher and Cameron Diaz? The end of the movie. She hit him, she's like, you know why. Oh, I like movies. Anyway, I digress. Another story for another time. So, what, anybody know why we call it continuous? Why we call it discrete?
Isn't it discrete like given values only? You can't change.
Bingo. It's a specific value.
Characteristic. Oh yeah,
It's
characteristic.
like an analog watch. None of y'all wear, none of everybody. See, it's that generation. Everybody, I'm in it too. But I know analog. But I'm just saying. Analog, right? You could count down to the seconds. Tick, 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 tick. Right? Whereas a digital watch can't get those seconds. I'm gonna get down to the minutes. Right? So that's the difference. Characteristic is specific. We just talked, you need at least 69. Each level shell has a set value based on the binding energy. So we call it discrete.
So characteristic is discrete.
Characteristic is discrete. Make them the same. They're one and the same.
And then Brems is continuous.
Continuous spectrum. Right? And then we'll draw them also to show you. I'm a picture person. I can remember a picture. Nobody's business.
Why did they describe Brems as continuous? Like the value could just.
Oh, that's what we were just gonna wait. So he.
Oh, sorry.
Did you go to sleep for like 2 seconds?
I was writing something down.
You see why you can't take notes in class?
Because you said it was specific for. So we're just doing Brems. Yeah, I still got it.
Okay, so here we go. This is why it's called continuous. We said what percentage of the beam is going to be Bremsstrahlung?
85.
85. What energy, what is the minimum energy we need to produce a Bremsstrahlung photon? Let's see if you guys got some
Minimum?
thinking. Any. That's the truth. I said you need a minimum of 69 for characteristic. I never said it was a minimum for Bremsstrahlung. So it can be created from energies as low as 0, which is nothing, to whatever the maximum value of kinetic energy you select on that console. So that is why your Bremsstrahlung emission spectrum looks like this, from 0 to whatever it is I choose, and let's just say this is 100. Continuous. I can get Bremsstrahlung photons anywhere in here because they don't have no minimum. The maximum there is. What did I select on the console? That's the maximum energy I can give. The maximum kinetic energy I can give those electrons. What time is it? 4. What time do we start? A little after 3:30. All right, I'm gonna try and wrap it up real fast because we gotta go through AC for y'all. Okay, we're almost done. So that's Brems. Characteristic. What I say was the minimum?
69.
Discrete too, right? Characteristic. That's why you got one peak. Because you need the minimum value. That's the only minimum that you need to produce that. So it gets a bar. A graph. What's that? The bar, yeah. And give it a one peak. And then, usually they'll put the 69 down there so you'll know. But that's the overall gist of the emission spectrum. Now, there are things that influence the way it will look. But that's the overall gist of it. Any questions? Come and talk to me.
So you need 69 to produce what?
We need 69 for what, guys?
Characteristic.
So that on the graph, does that just make like one photon or?
No, so because they're discrete values, you can have many energies within this. Why do I say that? And that might be confusing, and I don't want to make it crazy, but in that slide number 10 that I mentioned, that showed you all the energies. So K shell was 69, L was 10, M is, I don't remember them anymore, it's been a while. But everyone has a specific value. So remember we said if L fills K, how did you find the energy for K? You subtract it. But what if M filled this? You get a different value, right? So if this was like 6, then you would subtract these two. That would give you another number. But that's still all K characteristic photons because no matter who filled it in, it's still K characteristic, right? So I could keep going. I think the last shell is P, but you don't ever see an energy for P. I think this one is like 0 point something. I can't remember. 1, I can't remember. But anyway, there's many bars, and you'll see that indicated in Bouchon's textbook. he shows you a lot of slivers of bars, and that's because depending on which outer shell filled in the vacancy, it will take on that energy. But it's still K characteristic because that was the shell that was knocked out, right? That's why I said no matter who fills it in, it don't matter, it's still K, right? Does that make sense? Cool. All right, that's the gist of this overall. So, let's see what else. Oh, that's on slide number 35. So if you guys look at slide 35, you'll see it. You'll see like, how many bars in there for? 5 bars for K, because it really depends on who fills in. Does she show you in the next slide? I don't know. Nope, she didn't go into details. I'm not gonna go into details because she probably doesn't want you to know that. Yes, sir.
Why does it look like that? Like, why is the peak like that?
This?
Yeah.
Oh, I'll just do something. But it looks like a regular bell-shaped curve. Just, if you had to draw that, that's the general shape. It's a bell shape.
Would each graph be like different?
They do change based on what's the factor
Could you show
that's
us,
changing.
like what's under, like?
Right, so did we change MA? Did we
Yeah.
change KVP? Did we change filtration? Did we change target? So it depends on what the factors are. It will influence how it looks, but it still will always be a bell shape. This will always be a stick or a bar, but it will just change in its positions. I will show you that now. So if you look at slide number 36, that's basically what you see. And this just says, label, this is Bremshaw, this is characteristic. If you had to draw a general emission spectrum, could you do that?
Yeah.
That's general. But now she specifically asks you something about one of the factors, which we'll talk about, and I'm gonna mention it again, because I think it's on my, I think she has it as an added PowerPoint for tomorrow. We'll go over it again in detail. Okay, so let's see, what do we got? Emission spectrum, blah, blah, blah. KVP, so she talks about KVP, MA, and, oh my, more KVP is very long, target material. Oh, okay. All right. So we'll go over it because you have to, and we'll talk about it again really quickly tomorrow. Maybe not as quick as I'm doing it now, but we'll do it again. Okay, so, you know, why did I erase the whole thing? Y'all let me do that again. I need that. Oh, man, I cannot mess with y'all. Okay, so KEV is my photon number. Okay, so MA. MA controls what?
Quantity.
Well, it means quantity, yes, and it controls the quantity or the number of photons, right? Boiling off those electrons. We gotta always keep going back, remembering how everything's connected. So, if I chose, I don't know, 30 MA, that's just make a bell-shaped curve. I'm making a curve because it's gonna have that general shape. That's not gonna change. It will always be some bell. It's just a matter of where it's positioned is what's gonna change. So let's just say I said this was what, 30? 30 MA. Oh, 300, not 30, 300 MA. That's what it looks like. Now you have to always remember there's always gonna be a characteristic photon because characteristic X-rays is still being produced. Okay? So there should always still be a bar. It should always still be at 69. Because right now I'm talking about MA, right? So we should still have our bar somewhere here at 69. Now what if I increase my MA? I go from 300 to, I don't know, 350. I go to 301. I would say it really doesn't matter. Right, you produce more photons. Because MA controls quantity or number of photons. Whenever you think MA, you should automatically think quantity. Number of photons. Those need to be interchangeable words. They mean the same. It's like having too many nicknames. How many nicknames you got? Kenzie? No, not Kenzie. Sorry. You must have been thinking about something. Anybody got too many nicknames? Okay, doesn't matter. Anyway, all right. So if we increase our MA, let's just say we double it to 600. What's the relationship between MA and quantity? Is it direct? Is it indirect? Is it inverse?
Direct.
Direct. Directly proportional, directly squared, directly cubed.
Directly proportional.
Directly proportional. So that means if I change my MA by 2, then I should have twice as many photons. If I change my MA by 4, I should have 4 times as many photons because it's direct. The more MA increase, the more photons I produce. It's directly proportional. So if I change one, the other one changes identically. Okay. So if I went from 300 to 600, then I should have twice as many. It should still be the same. It should end in the same spot. So I'm sorry I didn't do so. But it should still end in the exact same spot because I didn't change my energy. I only changed MA. So if you ever saw them make an adjustment to MA and the energy moved, that's not right. Because MA only influences MA. MA does not change KVP or energy. Everybody still with me?
Yeah.
So this is trying to indicate twice as much. This would be my 600, right? If you had to draw a graph somewhere. You just want to show the effect. It's not going to be exact because we're not measuring it. Right? So that's MA. That's your emission spectrum. MA is directly proportional to the number of photons, to the quantity, to the amount. There's different ways to say amount, number, quantity. Right? And again, it's how they make tests, just using different words, but they're all the same. Right? This goes up by 3. If I increase my MA, I should produce 3 times as many more photons. All right, next one is KVP. Fun stuff. KVP is very long. What does KVP mean? What should you think of? What word should you think of when you think about KVP? Energy. What else?
Quality.
Force.
KVP. I'm gonna write them down because you should know them. What did somebody say? Energy. What else did someone say? Anything else? What else?
Quality.
Quality. Right? Not quantity. That's MA. Anything else? Should be one more word you should never forget. All 3 of them. They are all related. Begins with a P. Pound. What?
Power.
Power.
I said
Pound.
power.
No. Not power, yes.
Peak.
Not peak. When you change the KVP on the console, what are you doing? What's the purpose of it? He was doing that in positioning.
Penetration, right?
Penetrability.
Penetrability.
I don't feel like writing all the words, so I stopped. All of those you should always remember together every time, because you might see any of them on the test. And just because I use energy doesn't mean I'm not talking about KVP. Just because I use the word penetrability don't mean I'm still not talking about KVP. That's why I said you gotta know those key terms. Gotta know. Okay? All right. So, got that out of the way. So now, KVP. Let's just say this is my first one. And I used, 90 KVP here. Okay. That's the emission spectrum for 90. Okay. This is our characteristic photon because we still have one, right? We use 90 KVP. But we should still have a peak. Okay. Characteristic peak. Okay. So, that's 90 KVP. Actually, I should have wrote it here, but whatever. So now let's just say I increase my KVP. Actually, I want to go with a different number. I want to go with 80. Okay. All right. So now let's just say I increase my KVP. And I'm going to increase it to, 92, 90. Let's just go 90. It's time for 2 more. Okay. 90. What changed? Somebody describe what changed.
How far up that
Yes, the energy changed, right? We saw that. We went from 80 to 90. So check. That went up. What else? I know it's not the best drawing, but you can see the difference. I'll show it to you.
And also the number of photons?
Good. Number of photons changed. So my energy changed. My number of photons changed. Something else. Well, looking at the graph, like the picture. Oh God, that's so terrible. I'm like looking at the graph. They're like, we looking. We looking. You did a terrible job. This is not it, right? Where's my? There it is. What else looks different about it? you see anything regarding
It's a higher peak.
The
peak? The peak is different. Good job. E? Can I say that? E?
Yes.
Okay. I'm sorry to change your name. It's
No,
just,
it's okay.
I'm not doing good with your real name. So the peak is different. So if we look here, let's just say this is the top, highest point of this curve, right? This is the highest point. Well, where's the highest point of this one? It has shifted. That's how we would describe it, shift. It has shifted. Shifted which direction? Right or left?
Right now.
Right.
Oh, wait, the
Low.
bottom?
Yeah.
The peak.
Oh, the right one should.
Yes.
Oh, okay. I was looking at the bottom one, sorry.
He's like Beyonce, to the left, to the left. Okay. So when you increase your KVP, you've produced more photons. The energy is increased. And you can see the energy, the peak. The peak basically is indicating where the average, the most photons are being produced. Right? That's where most of them are. They're being produced at this level. And I believe Bouchon tells you that is 1/3 of the maximum energy. So what does that mean? That means if I have 80 kVp on this one, right, this black one, then this average energy, that means the average number of photons will be at this level because that's where the peak is. So it would be 1/3 of 80. That would be what the average is, if you had to calculate it. Do you have to? I don't know, I don't think so, but that's just if you had to. Same with the one that's at 90. The average photons, the average number of photons coming out of this beam will be at this energy. And it would be 1/3 of 90. It's the average of the energy, 1/3 of the energy you've selected on that console. That's your KVP. Here's your spectrum. Done. I know. What? How many times I read that, Miss Eva? Me too, when I was learning it, me too. Okay, another thing I want you to notice. My KVP went from 80 to 90. It's like what, 10?
Yeah.
Well, in actuality, hey Virtue, I wanted to come say hi, but I've been all
You're busy, I'll catch you later.
tomorrow maybe. 80, 90. Oh yes, 80 to 90. That is actually a 15% increase if you did the math. You learned about that 15% rule, right? Comes from changing KVP, right? 15%. That's why we make you learn it. That's not the reason. Well, we make you learn it for a reason. We use it on a daily practice. We just don't realize it. Here's how it goes. You didn't know it was 15%, but I told you. If you did the math, you can, right? Do you know how to do percentages really fast? Everybody? In the head real fast? That's how you do it. Everybody know how to calculate 10% of something? 10% of a number is usually that number. So what's 10% of 80? 8. 10%. 10% of 90? 9. 10% of 30? 3. Usually how it works. That's how you do math in head real fast. You didn't know that, I'm just telling you right now. Okay. Now, the other, it said 15%, but I was just showing you how to do 10%, right? So how do we get that other 5%? Take half of the number. So 15% of 80. So first you take 10% of that, it's 8, right? And then you take half of that number 8, and it's 4. So it'll be 12. And I wrote 92, but I said forget it, didn't I? I was like, let's just write 90. But it's in actuality, 15% is 92. So in order to calculate 15% really fast, because who got time to mess with a calculator when you on the test? First thing you do is take 10% of the value. Then the second thing you do is take half of the actual number of the number. I'm just write number. So if you want, you can do it on your calculator and you can calculate 15%. Everybody know how to punch it in on a calculator? Yes, no? Y'all don't be shopping?
No.
I'm a shop. I got a problem. It's a real problem. Especially when you have a child. Oh man. Anyway, Well, you should know how to do 15% rule. I'm pretty sure Christy said you must know it.
Yeah.
So then I highly recommend y'all work that out. Know how to do it on the calculator. You multiply whatever the value is, 90, let's just say that's the number, times 0.15, right? Because this is a percentage and you move it 2 spaces to make it a decimal. So you'll say 90 multiplied by 0.15, that's 15%, and you do the math, it should still be that same thing we just said. Well, it will be more than that now because it's 90, so take 10% of 90, right? Which would be 9, and then you add 4.5, right? Because you get a half, 9. Sorry. If the math is making you crazy, then that means you need to calculate. Try not to do the shorthand right now. But we do need to know what the 15% rule is. And the 15% rule says what? Anybody can tell me? Because you should know it.
If you raise it by 50%, the MAs get doubled, or does it divide by 2?
That's correct. So that's to focus on one direction, but a change in KVP by 15% is equivalent to either doubling your mass or cutting your mass in half. Okay? So if I were to increase my KVP by 15%, right? Let's just say that's what I did on the console. I went from 80 to 92. That's an increase in KVP by 15%. What that really means is it's equivalent to giving twice as much mass. And I didn't change the mass. I just said I just changed my KVP. So if I put on the console from 80 originally and I move now to 90, that's 15%, 92. That's 15% increase. That was almost the same as me increasing my mass by twice as much. Right? So let's just say, and I'll write it down for you. If I went from original, from 80 kVp, and let's just say 30 mass, that was my original technique, right? But now, I need to change it, and I want to increase this by 15%. Well, now at 92 kVp, right? That's 15%. Even if you didn't know, that's what that is, okay? Well, this change is equivalent to just changing this by doubling it. That's what that tells you. If you increase KVP by 15%, it's equivalent to doubling the mass, right? No? 15% rule I got everybody?
It's equivalent, it doesn't change it?
No. You can't change mass by changing KVP. Okay, they're two separate entities on that console, right? KVP controls force or energy. Mass controls quantity, number of photons. They're two separate entities. We need them together to balance out the image quality. You'll learn that in the other class. So, once again, 15% rule says, one way to say it is if I increase my KVP by 15%, it's equivalent to having doubled the mass. Another way to say it is if I decrease KVP by 15%, that's equivalent to cutting the mass in half. That's the 15% rule. I just said it to you in two separate sentences. You have to know that. You should be able to write that or ask that on a question, on a quiz. Because honestly, I would have it. With my quiz, you definitely better write that down. Now, the reason why this is important is because you just saw, before this, we did MA. And MA controlled how many photons. When you think about MA, you should think about patient dose. That's the point of it. MA controls the amount of dose that patient is going to receive. Right? So if just by increasing this, it's equivalent to having doubled that and made it 60. But I don't want it to be that much. That's a lot of patient dose. Between this, as we can see, KVP already increases the quantity. Just by doing this. That's not even touching this yet. Just changing my KVP by 15%. I'm almost giving my patient twice as much dose. Now imagine if I did use the mass. Right? That's a lot. I'm burning them. Not really. No, you are. You're hurting them. we have to be safe, right? We're dealing with radiation. We don't want to hurt our patients. Okay. So that's the 15% rule. So I would definitely recommend going back, looking at that. Check it out at RadTech Bootcamp. It's really great. They probably said it better than I did. Don't tell me if they did. I'm saying. But that's our 15%. And that's the importance of using the 15%. It allows us to adjust our beam penetrability, as you learned, because you need the beam to pass through the patient's body part. Some of those photons need to reach that image receptor. Some of it gets absorbed. But we need some of them to reach the image receptor. Otherwise, we would have an image that looks all white or all black. So we need some to be absorbed. We need some to reach the image receptor. What's the point of KVP and penetrability? That's what gives us the black and white that we see in those soft grays. Have you guys learned that yet? The contrast, high contrast, low contrast? Not yet? It's coming. Okay. I don't want to get ahead. All right. Anybody has any questions about KVP and the spectrum? What happens when you change a KVP? What happens if you increase it? What should you see? More photons? And it's not double the number of photons, it's just more. Okay? That's why we use the 15% rule. That's why we don't double it. Not like how MA is, as we just saw. And that's on slide, she has it here, slide 45. Went from 72 to 82, and we can show you that. Or she still has it on 44. Oh, I guess she starts talking about it way before that. 42, but yeah, 3. When she starts talking about it. Okay. Any questions? No? That's good then. I hope. I hope you're not telling me stories. All right. Next one was filtration. Filtration. Y'all learned? Did you do that in lab yet? Filtration? Filters? With Rich? I don't know if you did that lab. Probably not. It would probably be the next week because I'm teaching it this week. So it's probably coming out. Okay, so what is the purpose of a filter? You learned that in the earlier chapters. I know that. What does a filter do? What is this for? What's it for? You went over that in chapter 6, I believe, with the X-ray tube. You learned about filtration. You learned about compensating filters. You learned about, what other things did you learn about? Okay, maybe it's not. Maybe I'm teaching that tomorrow. My bad. Sorry. Okay, filtration. The purpose of a filter is to absorb low energy photons. Okay, absorb low energy photons. We said the majority of the beam is Bremsstrahlung, right? So if photons can be produced as low as 0, all the way up to the maximum of what you choose, you want to get rid of these low energy photons. Here's why. I want you to think about it. If I said we're gonna have 5 quizzes in this class, we got 5. You're like, jeez, you suck, Miss Ely. But I said I would drop the lowest grade out of those quizzes. So whichever one was the lowest, I'm gonna drop it. What does that do to your average? It's gonna make it better by getting rid of that lowest grade. That's what a filter does. By removing those low energy photons, it increases the average, right? Imagine if you got an 80 on one test, a 90 on one test, and 100. I said I'm gonna drop this grade. Well, your average just went from what looks like an 80 something to a 95. Just because I dropped one. That's what happens when I remove low energy photons. Increase the average energy of the beam. It's more penetrating because that's the energy of the beam. Energy is penetrability. Energy is quality. Energy is KVP.
How much is low?
We just use the term low. There's no specific value. Now, you will learn in the lab that if we were measuring the quality of the beam, then we need it to be it needs to be able to reduce the intensity of the beam. How strong it is, strength of it. We need to be able to reduce the intensity to half. But I will talk to you about that tomorrow.